Look at this simulation of turbulent fluid mixing inside an industrial cylinder. To an engineering student, understanding this kind of chaos takes years of grueling study, mastering highly complex physical phenomena. The methodology they learn relies on strict physical conservation principles and dimensional analysis. It is the practice of using advanced mathematics to predict and manipulate how matter and energy behave. The ultimate academic goal is finding perfect spatio-temporal scaling. Engineers want to take a chemical reaction that works perfectly in a tiny laboratory test tube and optimize every variable so it behaves exactly the same way inside a massive factory. But a flawless physical design is entirely useless if it fails a completely different set of laws. Achieving physical perfection in a CAD drawing or a mathematical model does not guarantee the project will actually be built in the real world. To understand why, we have to pivot away from physical variables like pressure and temperature and look at financial metrics. Capital acts as a rigid physical constraint on any engineering project. Think about how you measure the financial benefit of a university degree. When you assess its value, you have to account for opportunity cost, the actual income you lose while sitting in a classroom. Every engineering choice requires weighing a theoretical value against an actual, often hidden cost. This split-screen diagram illustrates a core economic constraint, the time value of money. The basic premise is that a single dollar today is worth more than a dollar in the future. Because money can be invested to earn interest, its value is tied directly to when you hold it. Because of this decay, engineers have to look at long-term projects differently. Every month a chemical plant is delayed in construction, the future revenue it generates loses value. Delayed time directly equals lost money. To build anything real, engineers must view capital investment and profitability as the second equation of their discipline. Let's look at a specific challenge to see how this works: scaling up a chemical reaction from a lab to full industrial production. This is a schematic of a plug-flow reactor tube. Engineers often choose this over a mixed-flow reactor because it minimizes the required volume while maximizing chemical conversion, as raw materials enter one side and convert smoothly to a finished product. To reach these optimal conditions, the critical constraint is finding the exact length to diameter ratio. A longer tube makes the chemical conversion more efficient and uniform, but extending that ratio creates a physical consequence. The longer the tube, the more the fluid drags against the walls, creating significant internal friction and a severe pressure drop within the system. Pushing the physical variables to their limit creates a mathematically perfect chemical reaction, but it introduces a fatal vulnerability for the project's real-world viability. Switch lenses and look at the financial reality of that long plug-flow reactor. Building it requires an enormous fixed capital investment: the cost of the land, the steel, the construction, plus the working capital required just to start the plant up. We track this using a cumulative cash flow diagram, which serves as the primary diagnostic tool for a project's survival. At the start of the timeline, this line plummets sharply into negative space. This deep red area is the Valley of Death. These are the early years of the project lifecycle, where land purchases, startup fees, and capital costs accumulate into massive debt before a single product is ever sold. Here is where the two equations collide. That severe pressure drop from the long reactor tube requires massive, energy-hungry pumps to push the fluid through. Those pumps drastically increase daily operating costs, flattening the plant's ability to climb out of debt. These high operating costs ruin the project's rate of return on investment. It pushes the payback period, the exact moment the plant finally turns a profit, unacceptably far into the future. The physical constraint of pressure drop and the financial constraint of operating cost are actually the exact same force. Failing to balance them guarantees the project will be rejected. Zooming out, we have to evaluate the entire macro life cycle of an industrial plant, from the earliest theoretical models all the way to recovering the salvage value when the plant is eventually decommissioned. Because these life cycles span decades, engineers use discounted profitability criteria for large capital projects. This mathematical process discounts all future cash flows back to time zero, putting every investment, operating cost, and future revenue on an equal footing. A scientist explores what is physically possible, discovering the absolute limits of matter and energy. An engineer's role is strictly defined by the real world. Their job is to take what is physically possible and optimize it within the rigid constraints of what is economically viable. True engineering is the mastery of both equations. You must master the physics to make it work and the economics to make it real.